So for this installment of statistical concepts, we're going to talk about the relationships among variables. And when we do that, we're typically talking about correlational research. The big thing to remember is that correlational research does not show cause and effect. It merely establishes a relationship. When we look at the correlational coefficient, it's usually a value that falls between -1 and +1. And it will establish the strength of that relationship between two variables. The positive and negative part of the correlation coefficient dictates the direction of the relationship. So you can have a positive correlation, which means that basically a small value can predict a small value of another variable, or a large variable predicts or is associated with a large value of another. So when you look at this chart here, you can see that arm span, if it's 160 centimeters, can predict height as 160 centimeters, or if it was at 120, arm span is 120 centimeters, then height would be approximately 123, 124 centimeters. So that's your correlation, that there's a relationship between arm span and height. Also have a negative correlation, and or I'm sorry, no. Now the one that is most often used as far as correlation, the statistic, is usually the Pearson product correlation. The symbol for the Pearson product correlation is a lowercase r. And it's basically the correlation of one dependent criterion variable and one independent criterion variable. So a relationship is expected between two variables, and in this situation it is linear. So you will see a linear correlation between which the two on C and D again are nonlinears. The two A and B, positive on the left for A and the negative correlation for B, are linear correlations. If we didn't have a correlation, you really can't do, you wouldn't use a linear correlation on R value. Now, when it comes to interpreting the strength of the correlation, so you get a correlation, an R number. If it falls in between 0.8 and 1, it's typically very strong. If it falls between 0.6 to 0.8, then it's a strong relationship. 0.4 to 0.6 is a moderate relationship, and 0.2 to 0.4 is a weak relationship. And then again, 0.0 to 0.2 is a weak or no relationship. So when we now look at the reliability or the significance, what we would basically do is establish an alpha of 0.05, establish the degrees of freedom, which is n minus 2. So if you have pairs of scores that are 10, n minus 2 is 8. And then you would go into the appendix in your textbook of table 3 and look at the correlation coefficients for significance at alpha of 0.05. And then the R, if the R is greater than 0.6392, you have a significant relationship. So the R in this situation is 0.925. In the table it's 0.692, so our R is greater, and that means that you have a significant correlation. Now you could have a weak R of 0.05 but still be significant. So you have to also, now you can have a very low relationship, but it could also be significant. It just means that it's still not, even though it's a significant relationship, it's fairly weak. So when it comes to interpreting, you would also calculate the coefficient of determination, and that symbol is r squared. It really interprets the meaningfulness of the correlation. Indicates the portion of the total variance in one measure that is explained by the variance in another measure. So the variance of one and its relationship to the variance of the other. So basically you just square the R. It's that simple, and it basically means that 49% of the variance of the GPA can be explained by the variance of study time in the situation or the example in the previous slide. So the stronger the correlation, the more variance can be explained. However, 51% of that variance cannot be explained. So even with a 0.7, an R of 0.7, there are many scores that can explain or many things that can explain the variance. And that's called the coefficient of alienation. So when you look at this, to kind of help explain the previous slide, if you have an R squared that's 0, no variance, the variance from one variable can't be explained by the variance of another. Of R squared of 0.25 with an R of 0.5, 25%. So that means the variance from one can explain the variance of the other. So 25% can be explained, but 75% cannot be explained. So if you have an R of 0.9, the R squared of 0.81 means 81%. So now you have a huge overlap here, and the variance of one can be explained by the variance of the other. And that's a very strong relationship. Now you can also use correlations for prediction. And when it comes to using the correlation for prediction, you're basically using regression, and you'll learn this really heavily, and I'm just going to go over it really briefly for the purposes of this class. So basically you're making a prediction from the correlation that you just did, the linear correlation. The higher the relationship between two variables, the more accurately you can predict one variable on another. So when we look at this, we develop an equation to create a regression line. And that's really what we're doing. We're taking the correlation and we're going to draw a line of best fit. And the higher the correlation, the more we can predict one variable on another. So typically what you'll see is the independent variable is on the X axis, and you can see in the picture on the right I've labeled X for high school GPA, and Y is the criterion or dependent variable. So when you look at this high school GPA, we're trying to figure out if high school GPA can predict college GPA. So you create the scatter plot of each individual scores, you create a line of best fit, and that's your regression line. So when we look at this, you can see that you could use this regression line to predict that high school GPA could predict college GPA. Now again, the higher the relationship or the higher the correlation, the greater the accuracy of our prediction. So you can use Y to predict from X, or what I like to say is you can use X to predict Y. The distance between our straight line or our line of regression line, is called the error of prediction. So what we do is we take those individual scores and we basically measure, if you will, how far they are from that prediction line, and that's your error of prediction or variance in prediction. You can also use what is known as multiple regression. Multiple regression now takes, instead of one dependent variable, all right, you're taking multiple variables. I'm sorry, independent variables. Instead of one independent variable, you're now adding in a second independent variable. So high school GPA was used to predict college GPA. So now what we're going to do is add in extracurricular activities to see if we can predict GPA. And in many situations, you can use this to increase your accuracy in your prediction of college GPA. So in theory, you are predicting an outcome from two rather than just one independent variables. And the multiple correlation coefficient symbol for multiple regression is a capital R. Now, when we look at multiple correlations, we can use the adjusted R squared. And the adjusted R squared is, so R was the measure of the quality of prediction of the dependent variable. R squared is the proportion of variance of the dependent variable that can be explained by the independent variable. In multiple regression, we have gender, age, heart rate, and weight to predict VO2 max. That's our R squared. Remember, we talked about doubling R, and then you get that R squared, which for this situation is 57.7%. So the independent variable explains, those four variables explains 57% of the variability of the dependent VO2 max. So what we would do is we come up with this adjusted R squared, and there's calculations for that, which I'm sure you'll learn in stats. But basically what this R squared means is it shows if we can, by increasing the number of variables, age, weight, height, rate, and gender, if increasing those numbers would actually improve the prediction. And so if you look at this next slide, I think it really shows how to interpret. So if we had those five variables, or we had five variables that we wanted to use to predict, we'll say again, college GPA, what you would do is you would look at the R squared, and then you look at the adjusted R squared, and what you'll see is the adjusted R squared will increase up to a point. So if you look at variables 1, 2, and 3, it increases up to 85.9, but then when you add in variables 4 and 5, it starts to decrease again. What this basically says is that you may only need 3 variables to predict college GPA, so the 4th and 5th you don't need, because it doesn't really increase the accuracy of your prediction. So when you start to look at multiple regression, you'll start to really look at these adjusted R squareds to determine if you should have or you need all 5 variables to predict college GPA. So there are some conditions. The biggest condition that you really need is that your variables need to be independent of each other. They need to be correlated to GPA, all right, to college GPA, but you shouldn't really have, or I'll use the VO2 max, your age should be correlated to VO2 max. Your exercise level should be correlated to VO2, but exercise level and age are not correlated to each other. So they need to be independent of each other and not correlated in order to be better predictors of VO2 max in these situations. The big rules in prediction I just kind of mentioned, they have to be correlated to each other, or I'm sorry, not correlated. The variables you're using to predict can't be correlated to each other, because that will, if they're not, and they're unrelated, they will be better predictors. Limitations to regression studies are its generalizability. So they are population specific. If you have a very strong multiple regression, all right, and it's used to predict a certain population, as soon as you try to take that model regression or multiple regression model to another population, it really loses its accuracy. So it's very population specific, and that's termed shrinkage, because it decreases the prediction capabilities or accuracy with the new population sample. The other thing is you do need large sample sizes to represent the population. And that's basically participants are 10 to 1 or higher is often recommended. So you really do need large sample sizes to do multiple regression. These are some additional YouTube clips that I found that might help explain linear regression and multiple regression. So I encourage you to take a look at those in preparation for stats class.